So that was what we call the definite integral. It's called the definite integral because we come up with a definite answer. What's the indefinite integral then? Well, that's when we don't come up with a definite answer. There's not numbers to substitute in. So really, it's the same thing. But instead of substituting numbers, I go, well, plus a constant. Because there might be other numbers there that I don't know about that when I differentiated, I got 0. So it's indefinite. I'm not sure what it is. Number 2 here is what we sometimes call the useful theorem. Because it's very useful. It saves you expanding out the ax plus b. If you've got a linear function to the power of n, it still will obey the add 1 to the power over the power rule. But the thing you've got to be careful about is you also divide by the coefficient of x. That's when you're dealing with linear functions, though. It's only true for linear functions. So I don't have to expand 2 minus 5x all cubed out. I could just integrate this straight away. Add 1 to the power 4 over the power 4, but also on the bottom of the fraction, coefficient of x is negative 5. So 4 times negative 5 is negative 20. So I get minus 1/20th, and it's already factorised for me as well, the other advantage of using this. They don't have to try and factorise the thing. It's very useful for something like this, because if I put that in index form, well, how would you expand out 3x plus 1 to the negative 2 anyway? But it still obeys the add 1 to the power over the power rule. Coefficient of x in this case is 3 on the bottom. So I get minus 1/3. Very useful for surds, because once again, how would you expand out 2x plus 1 to the power of a half? Can't do it. Add 1 to the power over the power, but this time we're also dividing by 2, the coefficient of x. And mere mortals would write it as 1/3 2x plus 1 to the power of 3 on 2. But of course us super mathematicians would write it as 1/3 2x plus 1 root 2x plus 1. Plus, of course, a constant. So we'll add that in.